I'm going to introduce Olinda, okay, and then she can share her screen and start her talk. Can you test your screen, Olinda?
Yes.
Yes.
Is it okay?
Yes, it's perfect.
Right, so I will stop to share it. Okay, well, you can take one.
Okay, so welcome everybody. It's a pleasure to have another online session of Chemforum. Today we have the pleasure of having Olinda C. Monteiro. Olinda graduated chemical engineering from the University of Porto in 1994, completed her PhD in chemistry from Universidade de Aveiro in 2003, and since then she has been at school. She was a postdoc until 2007, a Ciência 2007 assistant researcher, and between 2013 to 15, she had an assistant professor fixed-term contract. Since 2015, she's an assistant researcher, first as an FCT investigator, and more recently, she received a SEC 2018 contract. Her research has been focused in the design and synthesis of tailored nanocrystalline semiconductors, and she is particularly interested in functionalized nanotubular materials for the construction of nanostructured platforms for photocatalytical applications, mainly for emergent pollutants removal. Today, she will speak about Titanate elongated nanoparticles as versatile building blocks to design new photocatalysts. So thank you for accepting our invitation, Olinda. It's a pleasure to have you here, and so now you can start your talk.
Okay, thank you, Isabel. It's my pleasure. And can you tell me if you are seeing my screen?
Yes.
Okay, so good morning. I think you know I'm Olinda Monteiro, I'm from school, and I'm here today to talk about Titanate elongated nanoparticles. My job is try to convince you that these are amazing particles if we are interested in design new photocatalytic materials. So, but before I start with my presentation, I had prepared this information about myself, but I think Isabel already said everything about me. I started my studies in ISEP, and then after my graduation, I went to FEUP, University of Porto, and after that, I spent 4 years in the University of Madeira as an assistant. And then I continue my studies for my PhD in Universidade of Aveiro. Since 2003, I'm in school, first as a postdoc, and then as an investigator with different contracts. At this moment, I have a SEC contract, and I'm waiting to sign a more permanent position in the PrevPAR program. But let's focus in science. So during my PhD, I have performed several studies concerning the synthesis and properties of several semiconductor nanoparticles. And then when I went to school, I decided to try to use these materials for photocatalytic degradation of several pollutants. If we talk about photocatalytic degradation, we must say something about TiO2. We know that TiO2 is an amazing photocatalyst, but at the same time has some problems related with the small absorption of the sun radiation, and also due to the high recombination rate of the charged carriers. Because of that, we propose the use of Titanate elongated nanostructures. Why? Well, they are very similar from the structural point of view. We also have the TiO6 octahedra, like in TiO2, but in this case, they have a layer structure, so we have a higher surface area, And we also have this, this sodium plus between these layers that gave us the opportunity of change these ions for different ones and try to play with properties of this material. But of course, they have some similarities, and because of that, we also like to improve the performance of these materials. Why? Well, we can know the problems, so we can try to shift the absorption energy to the visible from the UV, or if we would like to play with the recombination rate, we can try to reduce this recombination, for instance, by trying to create some intermediate levels here in the forbidden zone of the catalyst. We have done a lot of work in this context. We haven't tried, for instance, modify these particles with metal by doping or by incorporation. I will show you in a few minutes the difference for us between these two cases. We also have some works related with the combination of the titanates with some metal nanoparticles, preparation of some nanocomposite materials, and in this case, the layout of the final catalyst is very important. We also can try to synthesize this particle using, for instance, some organic species. And more recently, we are trying to combine them with carbon dots and carbonitrate nanostructures. These are only some examples of the work that we have developing in the last years, but I would like to spend 2 minutes in this case. This is one of our most recent papers, and I think this is a very interesting work. Why? Because one day we went to the lab to prepare titanate nanowires, because we always have some titanate in the lab. And after synthesis, instead, we have a white powder. We have a very pale pink powder, sorry. So the first discussion was about the color. Is it white? Is it pink? No, it's not pink, it's white. So to avoid more discussion, we decided to test this powder in the photocatalytic degradation of a model pollutant. After this experiment, we were almost shocking because the results were amazing. These particles were much better than the ones of simple titanate nanowires. So why? Well, we tried to produce these particles probably 10 or 20 times, and we always had pink color, very pale but pink color. This was a kind of pink period in our lab. During months, we were not able to prepare titanate nanowires white. Okay, so going directly to the point, what was the problem? We were using a precursor, commercial product, that was 99.9% pure, but the other 0.1% of impurities had some ppms of iron and manganese that were responsible for this behavior. Imagine what we have done to tell this story to the reviewers of the paper. But I think we had success, so the work is already published. That was a very interesting study. So let's try to prepare to start with the beginning. We need to prepare the structures. Look, this TiCl3 is the one that when has some contamination, you will have some problems. I forgot to tell you, but we solved this problem changing the the source of the titanium. We are now using a different brand of the same compound, so we have no iron or manganese in the solid. So we prepare an amorphous precursor. After hydrothermal treatment, we are able to prepare titanate nanowires. If we put the same precursor in water, we will be able to prepare TiO2. Then, if we decide, we can change it for titanate nanotubes. The structure of these materials, we know that is this one. And also interesting is that if we want to decide to play with for instance, with the time and temperature of these experiments, we are able to prepare titanate nanowires, nanofibers, or nanotubes. So we have a kind of control over the morphology of these materials. But this is how to prepare titanate nanowires or nanotubes, but we want to modify these structures. So if we decide to add a metal when we are preparing the precursor, we will, in the final, we will have a doped precursor that we can use exactly in the same way to prepare doped materials. In this case, what we are doing, and of course, depending on the amount, we are replacing some of the Ti4 plus by the metal in the octahedron, okay? In this case, when we have doped precursor, it's not so easy to control the morphology of these particles. We are studying this process, but I can tell you that, for instance, that it's almost impossible to prepare nanofibers doped because we always have smaller particles. We are studying this point. But as I told you, we also have this sodium here in the interlayers. So why not try to replace it by, for instance, some metal? We just need to treat the nanowires or nanotubes in an aqueous solution containing the metal, and depending, of course, of the metal, because in this situation, size matters, of course, but we will be able to prepare or to introduce some metallic ions replacing the sodium. So, what is the easier way to modify these materials? We just need, for instance, try to replace some of the sodium ions by H+. What we need to do? We just need to put our material in an acid solution. We must be careful about the time and the concentration of the solution, and we will start to see the replacement of the sodium by H+. Of course, if we wait a little bit more time, in the end, we can have the total replacement of the H+ by the sodium plus by H+. As you can see here, the size of the dimension of this interlayer is a kind of shrinking when we change from sodium to H+. And this difference in the material are visible, for instance, in the XRD. In this case, it's also possible to see the difference in the interlayers. If we look for the high resolution TEM pictures, you can see that we are reducing the interlayer distance when you change from a solid only with sodium and only with H+. All of these are excellent photocatalysts, being this one, the protonated powder, the best one. So, but we can also try to think in doping these structures. Why? We just need to prepare an amorphous precursor. And we will be able, after hydrothermal treatment, to replace some of the titanium by the metal. As you can see here, the change of the octahedra changed. okay, to tell us that we have a doped structure. But nothing happens until now with this sodium. So why not try to replace the sodium? In the limit, once again, we can have a structure, a doped structure, with the H plus in the interlayers. We have tested this, for instance, with cobalt. We have prepared a doped sample, Titanate nanotubes. In this case, we have no changes in the morphology. I must say that this is not true for all the conditions that we can use, but in this case, we have no problems with morphology. If we look for the XRD, for instance, this is the peak that I told you that is very important and that tell us about the interlayer distance. So we look here, we have no shifts. So this telling us that all the cobalt is replacing the Ti4 plus in the structure. But if we look for the optical behavior, the optical spectrum, we can see that after doping, we have not only a shift in the band edge absorption here, but we also have the contribution of the DD transition of the metal, the cobalt. We tested these materials, for instance, for phenol degradation. Phenol, it's a very interesting model pollutant, and I think it's interesting because when we look for the spectrum of absorption of the phenol, and we look when we start the irradiation, instead we reduce the absorption of phenol, it seems that we start to increase it. Of course, this is not true. We're not producing phenol, but the problem is that we start to have the absorption of other intermediated products that absorb in the same range. This is interesting, but for me, the most interesting of this work is this graphic here, where we can see that all these systems are catalytic. But if we compare, for instance, the one with the sodium interlayers with one with the H plus, we see that the H plus is a better photocatalyst. We can also see that if we look for the doped samples, we also have differences in photocatalysis. And in this case, the best sample is have a doped and protonated sample. So until now, we know how to dope these titanate structures, but we can think about the possibility of replace the sodium not by H plus, but for instance by a metal, ionic metal, of course. So in this case, we start to have some replacement of the sodium by the metal. Of course, if we think this for the doped material, we can also do exactly the same for the pristine sample. And we will have, once again, the metals in the interlayer. In the limits, of course, we are able to prepare these structures. And these are very interesting structures. Why? Because in this one, that is the doped one, we have the metal replacing Ti4 plus, and we also have the metal that can be or not the same metal that is replacing the Ti4 plus. So we can have the same metal in two different positions, or I can have two metals in two different positions, okay? When we look for this one, this is a very interesting because this allows us to understand the role of this metal when it's only in the interlayers. Because when I do this, I'm only able to replace the sodium plus and not to replace some of the titanium, okay? So this is sometimes used to compare the results and to conclude about where is our metal. But we can think a little bit further. For instance, Why not to try to modify these materials with the different structures? For instance, organic dyes. So we have tested these 4 cationic dyes, and these are the results. In this case, we were working with the nanofibers. We have the protonated ones and ones with the sodium. And as you can see here, for the protonateds, we have almost nothing happens. And when we have the sodium in the interlayers, we have very different results. For this one, rhodamine 6G, it's easy to understand why we don't have nothing, because of course, we have 2 parameters that are important in these studies. One is the dimensions, of course, of the molecule. In this case, rhodamine 6G is not a flat molecule, so sometimes it's very difficult to play with it. And also important is the protonation equilibrium constant, that sometimes difficult the interaction between the titanates elongated nanostructure and this kind of species. So, and how about this? Where are these species? Are they in the surface, or are the possibility of they are in the interlayers? So we decide to study this possibility, and we decide to make some calculations, trying to put all the dyes that were immobilized in the structure. We put it in the surface, first as a horizontal orientation, like this one, or as a 90 degrees relation to the surface. We made the calculations, and in fact, we needed these surfaces that are much bigger than the one that I have in my material. So this telling us, oh, I don't have only a monolayer, I have a multi-layer adsorption, or we try to think about the possibility of have these materials, they are cationic, in the interlayers. Why not? We have the distance that we have, it's more than enough to accommodate these materials. And this situation was confirmed by XRB, for instance. As you can see here, once again, this is the peak that tell us something about the interlayer distance. And when we start to add more and more organic dye, we start to have a shift. So that's because this molecule are in the interlayers. Then we decide to combine these results with the doping. So we decide to modify a titanate nanotubes doped with cobalt. We decide to put it in contact with methylene blue in this case. So this is the optical spectra that we have. Of course, we have absorption of the dye. And as you can see here, the absorption of the dye, it's very high under this condition. And it's much higher than the one that we have for the pristine titanate nanotubes. In this case, we decide to test how stable are these structures. And as you can see here, we put it as a solid under UV radiation. Oh, sorry, this is after, this is before and after, before and after. And as you can see here, they are stable under radiation. And if we look for the photos of the powder, we can see that, in fact, when we are working with the cobalt titanate nanotubes, these samples are very, very stable, even under radiation. We can also think about modify these materials with some other semiconductor nanoparticles. For instance, some metal sulfides nanoparticles, using, for instance, a unimolecular precursor for the degradation and to obtain, as precursor to obtain the sulfide materials. And as you can see here, depending on the metal, we are able to have very different morphology, nanocomposites with very different morphology. I must say that here, these are small islands with very, very small crystallites of CDS. Why are these so important for us? Well, we are interested in the optical behavior of these materials. And as you can see here, when we use bismuth sulfide, this one here, we start to have absorption in all the visible range of the step. Also, bismuth sulfide is an excellent absorbent for cationic species, if we are interested in this point. For the CDS, it's perfect. We can see the absorption of the CDS particles and also the absorption of the naked surface of the titanates. In the case of zinc sulfide, well, if we compare it with the absorption of titanate nanotubes, they are more or less similar, but I must say that this combination is excellent when we are interested in reduce the recombination rate of the charge carriers. So that's why we use a lot the zinc sulfide nanoparticles. But sometimes we need to want more and more. So why not try to combine bismuth sulfide with zinc sulfide? We know that we have a narrow and a wide semiconductor. So why don't try to combine these two and the titanate nanofibers in the same system? We have done this and we decided to study the influence of the layout. So we decided to prepare at the same time zinc sulfide and bismuth sulfide nanoparticles. We decided to prepare first the zinc sulfide in the surface of the titanate and then put the bismuth sulfide and do the opposite. Of course, here morphology can help us. For instance, in this case, it's visible that we have much more zinc sulfide nanocrystallites than, for instance, we have here in this situation. All of these materials are photocatalytic, but I would like to show you the results about the combination of bismuth sulfide and zinc sulfide prepared at the same time. And we decide to use this material for removal of a dye, in this case, metal and blue. If we look for the degradation of this product using titanate nanofibers, so we have our solution, we have some absorption, and then we turn on the lamp, and okay, we start to see that the degradation of the dye is happening here, and after more or less 1 hour, we have no signal of the dye. But if we look for the same experiment, but using bismuth sulfide and zinc sulfide, what we see? We have our solution, and then we put this solution in contact with our material, and then we turn on the lamp. And when we turn on the lamp, our absorption was here. So all of this was absorbed in our material. To see better the situation, look, we are here when we turn on the lamp, and then follow me. 2, 20, 30, 45, 75, and so on. And now we are here for 3 hours, okay? So what's happened here? Because when I start the radiation, I also start to increase the amount of dye that I have in solution. And only after 45 minutes, I start to see the decrease of this absorption. Why? Well, first, we have the bismuth sulfide that is an excellent absorbent. So it's absorbing the dye. And after, 4 times 0. We start the irradiation. Of course, we have the degradation of the dye, but at the same time, we have distortion of the dye that is in the surface of the nanocomposite. And of course, in this part, during this period, the adsorption is higher than the amount of dye that has been degrading. Okay, after we start to have more degradation, we probably don't have more adsorption, more dye to be absorbed, and we will have the degradation of the dye. And this system, it seems very important for me. Why? Because we can think and use this material first as an absorbent, so I can take it, put it in contact with a pollutant system. We can remove the pollutant by absorption, and then we don't need a lamp, we don't need to be in the lab, and then I can take this powder, the water, it's already with no pollution, no pollutant, and I can bring this material for the lab, put it under irradiation, and I will be able not only to recover the material, but also to degrade the pollutant. So we can have a combined system that I think it's very interesting. And it's very useful when you use bismuth sulfate. So after these examples, I think you're ready to participate in one of these studies. So I would like to invite you to come with me to the lab and to participate in one of these studies. Advantage, you don't need to dress a lab coat, or you don't need to put a mask. You just need to follow me. Okay, so what is our goal? Our goal is study the effect of having nanotubes or nanowires modified with ruthenium. So let's start. We know that we must prepare a precursor, a doped precursor. We have 1% nominal precursor with ruthenium, and I think you already remember, you already know that we can prepare directly from the precursor. We can prepare titanate nanowires. If we prepare first TiO2, then we will be able to prepare the nanotube cell. If we look for the amount of ruthenium, remember we are starting from the same precursor. If we look for the amount of ruthenium that we have, we see that we have a lower value when we are talking about nanotubes. Why? Well, remember, this sample is prepared directly, so if we lose some metal, we have only one chance to lose some of this ruthenium during the process. In this case, we can lose some ruthenium here or during this process. So the fact that we have a lower amount in the titanate, it's okay and is in agreement with the experimental part of the work. Then we decide to see the surface area, PET surface area, and look. Under these conditions, as I told you before, the morphology of these nanoparticles are very stable. So we have almost the same surface area. That is not true when we look for the titanate nanotubes. We have a lower value when we try to prepare titanate nanotubes, and we also have a higher but not so higher surface when we have nanotubes. Why? Well, I don't know. We don't know, but if you can have an idea, remember you are participating in this work, so you can tell us your opinion. I think we know that when we have a dopant in the system, the morphology is much more stable. And this can be part of the answer, but not, of course, not all the explanation for this. But we know that we have ruthenium in our materials. The next question is, where is ruthenium? We know that we can have ruthenium in interlayers, or we can have it in the replacing the titanium. Okay, so the first thing that we must do, it's an XRD analysis. If we look for here, well, it seems always in the same position, but this is not true. Remember that we have a very, very small amounts of ruthenium. And if we perform the same analysis, but with more time, we can see that, in fact, for titanate nanowires, we have a slightly shift in this peak here, saying that something happens in the interlayers. We don't have no news from this point of view, of course, when we look for XRD of titanate nanotubes. This seems that we have no changes in the interlayers, okay? So we are not expecting to have some ruthenium for the titanate nanotube samples. But we need to know more about this metal, so we decided to analyze the samples by Raman spectroscopy. And what we discovered, that for titanate nanotubes, the spectra are similar. We have here the vibrations, they are exactly the same. When we look for the nanowires, we have some changes here, okay? So we have some shifts in some of these peaks. What was our next step? Well, we decided, remember when I told you that it's possible to prepare a titanate nanowire samples with a metal only in the interlayers. So we decided to prepare a sample with the ruthenium only in the interlayers. And then we analyze the sample by Raman spectroscopy. And in fact, when we have the ruthenium in the interlayers, we can see that we have some shifts. And these shifts can explain why, for the nanowires, we have shifts in this material. Okay, so for titanate nanowires, we know that have some ruthenium in interlayers. We need to know where is the ruthenium in the nanotubes, because we know that we have ruthenium there. So we decide to do an XPS analysis, and what we can see here, we have no ruthenium binding energy, so we have nothing with this kind of connection. We have a shift here in the peak of titanium. Sorry, it's missing here. This is titanium to P. We have a shift in this peak, and this is telling us that we have some changes in the environment of titanium, and this is explained by some replacement of titanium by ruthenium. Using XPS was also possible to confirm the presence of the ruthenium, not using the usual 3D peak, because in this case ruthenium overcomes with the carbon peak. But we decide to look for this peak that is a little bit smaller, but confirms the presence of the ruthenium in our samples. Then we decide to study the optical behavior of these samples. As you can see here, we have a slight shift in the absorption edge of these materials. And when we combine these results with the ones obtained by the valence band, XPS valence band spectra, we can see that we know exactly where is the position of our valence band, conduction band, and of course band gap. Okay, and this is very useful because telling us that in fact our metal ruthenium can be here in forbidden zone and can act as a scavenger, donor or acceptor type, depends on the position of the level of the energy. Okay. Then, with all these results, we decide to study this first for caffeine degradation. And as you can see here, our best result was obtained using the Titanate nanotubes. As you remember, this is the sample with the lowest amount of ruthenium, and this is the sample from the doped samples, the one that presents a lower surface area, but is the best photocatalyst. Of course, for these studies, not only is important to degrade the pollutant, but it's also very important to analyze the byproducts, the intermediates that are formed and degraded during the irradiation. And as you can see here, the difference that we have in the performance of these two materials, the difference is not only related with the surface area, for instance, because when we look for time profile of the degradation products, we see that the mechanism of degradation in both cases is different. We have different intermediates when we are using the Titanate nanowires or the nanotubes. We decide also to investigate these catalysts for the sulfametazine degradation. In this case, it's not so obvious the difference between the ruthenium titanate nanotubes or nanowires. The system is very fast. After 30 minutes, I have no sulfametazine in solution. But once again, when we compare the profile of degradation and formation of the byproducts, we can see that we have very different performances. For instance, after 90 minutes, I must remember you that sulfametazine is degraded after 30 minutes. We need more 1 hour to have no byproducts when we use the nanotubes. And for this, we need more time to degrade these byproducts. So, but they are catalytic. So we would like to know why are they catalytic? Because they absorb in the visible, or we are playing only with the reduction of the recombination. So let's try to see what's happened when we use the visible radiation. The conclusion is the same for caffeine or for the sulfametazine. And as you can see here, of course, this all the process is slower because we have less energy, of course, but it's obvious that when we have the doped samples, we have an improvement in the photocatalytic performance of this material. So they are active under visible light irradiation. About the recombination, these are the photoluminescence spectra, and as you can see, in fact, when we have the ruthenium in the system, we have a decrease in the emission energy of these particles after irradiation. So with all this information, we were able to propose a mechanism of photoactivation of these materials, where we have the influence of the ruthenium ions here in the forbidden zone, and that improves a lot the photocatalytic performance of these materials. So now it's time to look for the future. At Isabel and I'm starting a new contract as an investigator. I must say that I'm also waiting to sign from PrevPal program, but at this moment I'm interested in this project. The title of the project is an integrated solution for the effective removal of toxic metals and pharmaceutical and personal care products from wastewaters. What can I say about this project? Well, as the evaluator said, its main objective is to supply an integrated solution to remove simultaneously heavy metals and emerging pollutants from wastewaters. Of course, we intend to do this using this kind of titanate elongated structures. As probably you know, this kind of projects have no money associated with them, so we already submit a proposal for financial support, a project proposal. We already submit a PhD grant in the last fall to find someone to work in this topic. Of course, this is a position that was submitted in 2017, so 3 years ago. At this moment, we already have some results related to this topic, but it will be for my next presentation. And about this white page or half page, well, I think the future must have this half white, not this page. Why? Because here, of course, we are interested not only in use these materials for the photooxidation of pollutants, we are interested in start to write here some other topics. For instance, use these materials for other applications. Why not only to degrade by oxidation the pollutants, but why not try to use these materials for other processes to create some new products, or to try to use them for already used oxidation process. So if you have an idea, if you have any system that could be interesting to test with these materials, well, we can discuss it, and we can start to write it here in this part of the future. And with this, I will finish. I would like to thank you for being here, and that's all. Thank you.
Thank you, Olinda, for this very interesting talk on a quite different topic, at least for me. So the talk is now open for questions. Irmelinda, do you have a question?
Yes, I do. Hi, Olinda.
Hello, Irmelinda.
Nice talk. Thank you very much. For somebody who is out of this field, I have a question.
Yes.
I guess, and also provocative comment or question. The question is about naive question is about what are the illumination conditions or irradiation conditions in which you test your materials? You mentioned that some of them they respond to visible light, so they have photocatalytic activity under visible excitation. I would like to know if you use some sort of solar simulator, because I think people are now very interested in using the sunlight.
Yes. Okay. So
I can just make the second question, and
if you want, you can. Yes, please. Sorry. Yeah.
The second question is about artificial intelligence in the lab. It's this question.
We don't have.
Yeah, I know, but I think artificial intelligence can make a really big impact in your field of work in material design and characterization. It can help with the automation of the process and in the decision making. And so I would like to know your opinion. If you see that coming to your lab in the near future, or what you expect for the impact of this new approach to materials design. Thank you.
Okay, thank you, Olinda. So about the radiation sources that we are using this kind of materials. First, we start with a mercury lamp because we need to decide if the materials are catalytic or not. So we use a strong, very energetic power source of irradiation to test the materials, and then we decide to decrease this amount of radiation. How? Well, we can use a filter, borosilicate filter, and we start to cut some of the UV radiation. Then we can use a xenon lamp. We also have some xenon mercury lamps. And in these cases, we are also able to perform the experiments using borosilicate reactors. So we are cutting almost all the UV radiation. Okay, in some limits, no, I think not on, in these examples, but we also are able to perform some experiments under sun radiation. Not this year because we have some limitations, but usually we can put our things in the rooftop of the building and do our experiments, for instance, during June or July, depending on the days, of course. I don't know if I answered your questions.
Yes, thank you.
Okay, so depends if materials, sometimes we test materials and they only work under UV light, so, but we always start with UV visible light, okay? About the second questions, well, I have no answer for you. I think it's very interesting when you think you have the power in your hands. When you understand all these small things and how big is your power to play with these small pieces, with everything. But of course, we don't know nothing about these materials. Well, we know a little bit, but there are a lot of questions that need to be answered. And sometimes we need probably more collaborations with people from different areas that help us to understand these points. Okay, I think it's only like what I can tell you.
Yes, indeed.
But thank you.
Thank you. Isabel, you're talking, but
yes, we are not hearing you.
Okay, I was asking if somebody else has any questions for Olinda.
Hello.
No?
Hello.
Hello?
Yes, can you hear me? My camera is not working.
Okay, it's Anu.
Yes, yes, yes.
Okay, you can make your question, please.
Okay. Olinda, thank you so much for a nice presentation. I have some queries. Hello, is it audible?
Yes, please.
So like in some of the papers, I've noticed that when we design some materials for the removal of organic pollutants, we generally calculate band gap. Is it really necessary to calculate the band gap, and why it is necessary? Like what kind of information do we get from the band gap calculations?
Well, the importance of to know the value of the band gap, it's because you need it to, for instance, if you know the position of the valence band, you need to where you will have the conduction band, and for that you need to have the band gap value. Okay,
Okay, so it means a higher band gap will signify that the absorption property of the material will be higher, something like that?
No, the material will be active with only with a higher energy. For instance, more in the UV region. Okay, if you have a material with a very low band gap energy, you can activate it under, for instance, under visible light.
Okay.
But if you have a material with a high band gap energy, you must have more energetic condition to activate it.
Okay.
I don't know if I answer your question.
Yes, 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 thank you. And I have just one more question. It's like we usually calculate the band gap using a solid state UV or DRS. Is it possible
If it is possible
also
to
to
use,
calculate band gap using photoluminescence?
yes, yes. Usually we use the DRS spectrum, but of course you can use the photoluminescence spectra. If you have the excitation and the emission spectra, you will be able to calculate the
Band gap.
band gap. Yes.
Okay.
If you have some doubts and if you want to send me some email, I can help. I don't know.
Okay, okay. Thank you so much. I'll contact you then over email.
Okay.
Thank you. Thank you so much.
Thank you. Any more questions? Any more questions? No, maybe I have just one small question. There's some interferences, sorry.
Yes.
You showed an example in which absorption occurred. And
sorry, can you repeat, please?
You showed one example in which the dye was absorbed to the material.
Yes, absorption, yes.
But that was not a problem.
No.
Even a technological advantage in somehow.
Depends, yes.
Are these materials usually good for absorption, or that might be a problem, or?
Well, if you are interested in use this kind of materials for pollutants degradation, if you have absorption of pollutant in the surface, it's perfect for you. Probably it's even better if you have no absorption. But you must be careful in the end of the process to be sure that you will analyze what you have in the surface of your materials. Because of course, we want to degrade the pollutant, but we don't want to remain, the pollutant remains in the surface, okay? But it's perfect if you have absorption. And for instance, in the example that I gave this morning, you will be able to have two separated situations, only regarding the absorption, and then, imagine that you go to the, not the river, but, well, where you have the pollutant, you will take all the pollutant with you, and then you will recover your material in the under irradiation. So, from my point of view, it's perfect. You don't need to buy a lamp. You can buy the absorbent material, you can treat your water, and then you can pay to someone recovered material, and you can use it again. Okay. I don't know, I think it's an excellent idea.
Yes, I think so. Thank you, Olinda. Do we have any more questions? Well, if not, I think it's time to thank Olinda for this very interesting talk. I would also like to thank you for attending and wish you happy holidays. Okay, yeah. We'll be back in September and hope to see you all again. Okay, enjoy your holiday time.
Thank you. Have a nice holiday too.
Bye.
Bye.
Bye.